a brief look at a reference system, and then my colleague Mo will now come in with a specific case study, and we're using that to do a load profile design. So after that, we'll now give you further information with respect to our webinars. So I believe we will all enjoy this webinar, and then as we continue, we will now start with the first topic, which is the Fronius energy flow management. So basically, when we mention this, we mean using the basic Fronius equipment or devices or inverters, as you call it, together so as to properly analyze your system or your load consumption, so that by so doing, you will be able to say design a very efficient system. I'm just trying to break it down to a very understandable level. So as we can see here, we have different inverters. It could be a Gen 24 inverter, it could be any SNAP inverter, it could also be a TAURO. So when you want to do a design, system design, you would have to understand how the load profile operates or what the load profile is. It could be that there are peak periods when you have lots of loads turned on. So you want to design your system such a way that it could accommodate these consumption from these heavy loads. So in order to do this, you would need a smart meter, of course. You would need an inverter, a smart inverter, of course, which the Gen 24 and SNAP inverters offer. Now, for the SNAP inverters, you would have to make sure or ensure that it is one that has data manager. In case you're using one that doesn't have a data manager, you could as well use a data manager box. Or in the case whereby there isn't any inverter yet, and you just want to do a load profile to now figure out how the system design will go, you could of course use a smart meter and a data manager box. So this is possible. For the Gen 24 inverter, it's already integrated. The pilot is already integrated, which is the DATCOM unit, the data communication unit. So you'd have to use the Gen 24 inverter with the smart meter, because with the smart meter, you get a wholesome view of the consumption, and then that gives you a good idea of how the consumption is for that particular load system. So this is basically the first step in any system design, which is profile analysis. And then next step is now to control these heavy loads. It could be an EV, it could be an air conditioner, a heat pump, say a heavy duty washing machine for industrial purposes. It could be any heavy load. But then most important thing is, by the time you've gotten all the information you need from your load profile analysis, you would now be able to control these heavy loads in a most economical way, and of course that will ensure maximum self-consumption. Then afterwards, you can also utilize the surplus obtained to store energy in a battery, or of course as in form of hot water by using the own pilot. So that is just a summary. So let's get into more detail. And this, of course, explains what we mean by Fronius energy flow management. So to buttress on this point, load management simply entails using the digital input-output ports or terminals to achieve two main purposes. First of all, to increase self-consumption or maximize self-consumption, and then secondly, to reduce peak loads. So meaning that it operates in such a way that it turns on when in terms of maximizing self-consumption, and then turns off consumption when or during peak load periods. Yeah. So just by definition, peak loads usually is defined as a period when power consumption is at its peak and then in very high demand. So this usually comes with high tariffs. So it of course varies for different regions and countries. And of course, people or consumers would naturally want to avoid such periods. So with this profile load management, we'll be able to avoid this. So we'll be seeing that in subsequent slides. So, and secondly, after achieving load management, we can of course use the inverters and smart meters and data manager box to also achieve dynamic power control, which is a stepless control of surplus power to store energy in a battery and of course use it to utilize or generate hot water. So generally, the purpose is to increase or maximize self-consumption and autarky, or otherwise called independence, power independence, and of course, avoiding peak loads in combination with a battery storage. So let's now take a look at profile analysis. So the first step, of course, is to do your design. And I brought up this illustration to show us how this can be achieved by giving us a theoretical explanation, that is using digital input-output ports to control a load, of course, in order to maximize self-consumption and, of course, avoid peak load periods. So this is basically a single line diagram of how this can be achieved. Let's say we're using a Gen 24 inverter. We can actually achieve this by connecting an external relay to the already programmed input-output port. And then this now serves as the signal source for this particular heavy load. It could be an EV charging point or say an air conditioner socket. So this is basically how it is. So the live comes and then it's now connected to the contact point, but then the coil of the relay is energized from the digital input-output port of the inverter. So once it energizes, power now goes through the contact point of the relay and then energizes the load. So that's basically how it goes. So, and like I earlier defined, peak load are usually short periods that electricity demand is of a high demand. Yes, electricity supply is on a high demand, and consumers would preferably want to avoid this period because at this short period, the tariff are usually pretty high, higher than the normal tariff. So in order to achieve this through load profile analysis, we can of course limit or shave off this peak load, as you can see from this graph, such that say this EV is charging, we can of course interrupt this charging and ensure that it's not charged during this peak. Load period. So I've already earlier explained how we can actually achieve this using the inverter via its digital input-output port, and of course energizing an external relay or contactor. Yes, you can also use contactors because conventionally contactors have higher current carrying capacities than relays, but then depending on the amperage of your load, it will now help you in making a decision of which device to use, either a relay or a contactor. Okay, so having said that, we already have known the required components. You need, of course, the Gen 24 inverter or the SNAP inverter, whatever, either a SIMO or an Echo, or even a TAURO. And then, of course, you need a smart meter. And then you can now be able to do analysis via the Fronius SolarWeb. So, taking a closer look at a profile, we can see clearly here that that a peak load shaving is taking place. Now, this is designed such that you don't go above a particular load marking or load point. So for this illustration, we can now see that for this case, it's for an EV. As you can see, it's a wall box controlled by Fronius load management. So wall boxes are usually points where you connect EVs. So for this point, say the owner of the EV comes back home at about 3 p.m. and then starts charging the EV in preparation for work, say the following morning. And then when it comes to this point, it happens that this is a peak load period. That's about 6 p.m. to about 6:30. So we can see obviously in this case that the EV charging was interrupted so as to avoid this peak load period. So that's how load management can actually play a very important role in saving you lots of money in terms of paying higher tariff at this particular period. So as you can see, after the peak load period, it's of course stepped up and then continued charging the vehicle. So another example is in the case where we have a normal office working day. You have, say, you have air conditioners on, and then we have 2 integrated EV charging points of maximum charging capacity of 22 kilowatts, all controlled by a Fronius load management outputs. So the target here is to avoid peak loads higher than 50 kilowatts. So for this, you can see that there are certain points when the EV isn't charged, where all the EVs aren't charging, only one is on. So as we can see at this point, when the PV production, obviously it's been superimposed by the general consumption here in gray, but the color green here is the PV production. And as we usually know, it usually takes an ellipse, half ellipse shape. So for this period, when the PV production is low, it reduces the charging power to 22 kilowatts. That's from 44 that it's supposed to be. That's for the maximum charging capacity for the 2 EVs. So you can see in this case that it automatically drops it to 22, meaning that just one EV is charging at this point. But when PV production is higher, both EV charging points are engaged, and they both charge at 44 kilowatts power rating. So during target, once the 50 kilowatts target is reached, of course, both EVs are knocked off, both EV charging points are knocked off, and until it is suitable for charging again. Once that condition is reached, then it both comes up again. And then at the period when the PV production is going down, or in the evening per se, we can also see in this case that only one EV charging point is triggered, so the other is put off. So this is how we can integrate all these heavy loads into our PV production to ensure that we maximize self-consumption and, of course, reduce much avoidable tariff from the grid. So what settings do we need to achieve this? So in the meantime, please send in your questions. I will be glad to answer them either during the webinars or just after the presentation, and we'll be glad to attend to your questions. So continuing, the components needed, as earlier stated, your Gen 24 inverter, your Fronius SNAPINVERTER, either an Echo, Primo, SIMO, but ensure that it has a data manager. And then, of course, Fronius TAURO can also be integrated. And then, of course, you need a smart meter and then 12 volts relay. So this is very important. The rating or the voltage that the signal emits, that's from the digital input output port of the inverter, is a 12 volts rated signal. So ensure that your external relay is 12 volts rated DC. And if you're using a contactor, also ensure that this specification is met. Okay, so viewing it from the SNAPINVERTER point of view, this is where it's located, just underneath the inverter. Just having a close look, this is how it looks like, and then this is the digital input output port. We have 4 input output ports that can be configured for load management, as you can see. So that's for the SNAPINVERTER. For the Gen 24 inverter that uses the pilot as its data communication unit, same with the TAURO, it implements the same thing using the digital input output port. It's also 4 in number, input output 0 to input output 3, same with the SNAPINVERTER. So, and then coming to the web interface, if we want to configure this, we would have to first of all come to input-output mapping. So this is where you're going to configure a particular digital input-output port to a particular load management regime. So meaning that you could have 4 different loads being programmed using certain specific settings. So say we select this, which usually comes as a default, that is digital input output 1. It's usually selected first as at default. So you can do that, but whichever one you wish to select, whichever digital input output port you wish to select, ensure that you click on this tick mark to save these settings. If not, it's not going to be saved and it wouldn't be implemented. So after that, you would now go to load management. So now this is where you impute your settings. Just before you do that, I'd also like to inform you about the load or energy management priorities. So here you can actually switch between these priority points: load management, input output, battery, and then home pilot. So this means that for every surplus that is generated from your PV that you want to utilize, for this particular setting, the load management takes first priority or highest priority, followed by the battery, and then the home pilot. So that's what it means. And this is, of course, very changeable, meaning that you can take load management to either the second priority or the lowest priority. So after having said that, let's now come to the configuration and settings. So you could as well decide to name it. So let's say this is the configuration to control the air conditioner. So it's abbreviated aircon in this case. And then you'll now have to select how you would want your load management to function. Should it function by power production or should it function by power surplus? So if you choose power surplus, it means that it would be triggered with respect to specified surplus power or surplus feeding limits. So now we go to the threshold, which is where we impute the figures. So for this case, the control or the air conditioner comes on when your feeding power hits 1,100 watts or 1.1 kilowatts. And then it will turn off when your consumption is 100 watts. That's base consumption. So this is the threshold on and off conditions for your air conditioner to come on. So it will come on when your surplus hits a figure or the value of 1.1 kilowatts, and then would go off when your base consumption hits 100 watts. That's for this particular settings. And then you could also configure it to function for a particular duration. I think the minimum duration is usually 1 minute, and maximum, I think it's up to about 1,500 minutes. So this, of course, you can configure to your need or specification. So that's basically the condition for on and off in order to control, for this example, the air conditioner. So, basically this was for maximizing self-consumption. So looking at doing the same thing for, in this case, managing or shaving off peak load, or say peak load balancing. So in this case, it's a bit different than the initial or the previous slide where I explained. So in this case, it comes on when the surplus hits 1.1 kilowatts. Nothing changes from the previous slide. But now the difference comes in here. What you set here is that limit that you don't want your consumption to exceed. So it could be 3 kilowatts, as you can see from this example. It could be 4 kilowatts. It could be 5 kilowatts. So you will set that condition or that power limit that you wouldn't want your consumption to exceed. So that's how you're able to manage peak load consumption. So once your consumption hits 3 kilowatts, it will cut off, and then you wouldn't be using these heavy loads during these peak load periods. Of course, you can also set your time as explained earlier. So, yeah, by the way, that was for the SNAPINVERTER web interface. So this is for the Gen 24 TAURO activation, of course, using the Fronius Start app. Yeah, so the same thing applies. We have digital input output ports 0 to 3. Same thing applies. You would have to enable load management, select the pin that you want to make use of. And then when it comes to the controlling, you would have to select the condition either by production or by surplus. So in this case, you select by surplus. And then for this case, of course, you're free to configure it based on your analysis, your load profile analysis. So in this case, for this example, a feed-in condition of 1,500 watts or 1.5 kilowatts has been set as the on threshold, and then the off threshold is when the consumption hits 1,000 watts. So that's when it turns off. So let's now take more example to really drive this home and understand more what or how we can achieve peak load balancing. So in this case, we're using an example with EV, and in a case where we have PV production, that is PV surplus. So for this particular graph, as you can see, we have an off threshold of 4 kilowatts. So it's in negative figure because we are consuming from the grid. This portion in red represents PV production. So here, the EV charging is configured for 3 kilowatts. So but the threshold for turning on is 2 kilowatts. So once the threshold is reached, which is 2 kilowatts, the EV starts charging. And then it only goes off when the consumption, total consumption, hits 4 kilowatts. That is when you're consuming 4 kilowatts from the grid. That is when the EV charging goes off. So that's basically the explanation of this graph. And this is basically for during irradiation, during the day when you have PV, you have likelihood of having PV surplus. So how about at night time when there is no PV surplus, or maybe in the evening, or maybe during long periods of overcast? So the same condition is set. As we can see, the same threshold is set for 4 kilowatts, but in this case, a base load of 500 watts has been set or can be set. So it means that once the base load is 500 watts, it serves as the on threshold condition, so the EV starts charging, but of course goes off once the consumption hits 4 kilowatts. and then it goes off until the base load condition is met again before the EV can start charging again. So that's basically how you can put these settings into play. So let's now conclusively to take a look at a reference system. So once again, you have an EV charge being managed using the load management function. So in this case, there is no battery. Yeah, so to maximize self-consumption and of course to avoid peak periods or peak load, we can see that at this point, the EV charging was interrupted. And there is an equivalent graph here for power consumption, as you can see, grid power consumption. So once the point or the maximum configuration was reached, that is 4 kilowatts, the EV charge was interrupted until the consumption came down before charging now continued. So this is quite easily seen. And this is for a case without battery storage. And in a case where we have battery storage, it's much easier and much advantageous per se, because the battery tends to cover up for these peak load periods. As you can see, the power from the grid, okay, sorry about that. It's actually represented in red, but I guess it was chopped off here. So yeah, as you can see, the power from the grid, which is represented with the red color, is pretty minimal all across this production or PV production period. As you can see them, they appear very minimal, meaning that these periods have actually been covered from the power drawn from the battery. As you can see, power from battery represented with the yellow color. So in this case, if you have a battery storage system, you can of course achieve peak load balancing using the battery storage and ensure that you consume very minimally from the grid, and of course maximizes self-consumption, and of course ensures self-sufficiency. So with all this, I can basically tell you that Fronius comes with a lot of advantages as it comes to avoiding high consumption costs because of customers that have peak load measurement. So it helps them to avoid high consumption costs. It tends to help you avoid high network adaptations, meaning that you don't have to do recabling, reorientation of your loads, because this can be basically be controlled by using the digital input-output port of the inverter. And then, of course, this can, of course, be achieved with standard components, SNAP inverters, the Gen 24, the TAURO, the SNAP inverters, of course, with the data manager. And of course, you'd have to use a smart meter and an external relay or contactor. And then, of course, you can always get support from the Fronius support hotline in any case of inquiry. So that I believe brings me to the end of my presentation part. So, but before I hand over to my colleague, Mohammed Sidat, I would love to ask a poll question. So I'm going to launch it now, and I would like us to give our answers to it. So the question is, apart from Fronius load management, load profile management, how do you usually analyze load profiles and implement peak load shaving? The options, we have 3 options, by manually observing the consumption and then doing your calculation. Secondly, by using grid meter readings or other manufacturer algorithm. And then finally, by not doing any analysis at all. So I would be really glad to have your answers to this question. And I will be closing it in a few seconds and then sharing it with you. Okay, I will be closing it in say 10 seconds. Thank you very much for your answers. Great. So I will be closing it now and then sharing the answers you've provided. So I believe we can see the answers to the poll question. So 17% say they do manual observation and calculation. Quite a high percentage, 72%, basically use grid meter readings and then other manufacturer algorithm to achieve load profile analysis, and then 11% don't do any analysis. So thanks a lot for your answers. And at this point, I would want to advise that it is pretty important that we do profile analysis so that we'll be able to have a wholesome idea of how our load consumption goes, and then we can now make an informed decision on how to design our PV systems, especially using Fronius inverters. So at this point, I've come to the end of my part of the presentation. I will now be handing over to Mo, who will be continuing with his part of the presentation. So Mo, let me now hand over presentation.
Okay, thank you, Cyprian. Okay, we will now have a look at the load profile design. So firstly, we're going to look at an application example. So we're going to look at sizing PV for application with batteries. So what I have over here is a typical bell curve of a PV system. As you can see, the PV system starts to produce at around, close to 6, 7 a.m. Okay, this is where you can see the production ramping in, and as you can see, it peaks, between around, 12 p.m. to about 1 p.m. And then, following on so forth till about 5:30, 6 p.m. Okay, this is a typical load profile. As you can see, as a design engineer, you would like to get the majority of the day loads of your consumer within this bell curve. Okay, obviously we can't really cover the night load with direct PV, and this is where you need to size your batteries to correctly, cover your night loads. Okay, as you can see, your night loads occurs in the early parts of the morning and also in the latter parts of the afternoon into the evening. So there are 4 main parameters that you would need to look at. This is your energy production in the day, your energy consumption, at night, your peak load current, which is very important. It's very important to have a look at your peak load current. And this is because you always need to take into consideration the likelihood of the grid not being available. Okay, as you know, there are certain parts of Africa where the grid is not very stable and where we have frequent, grid outages. And, sometimes when you size a PV hybrid system, maybe you, for some reason, don't look at the peak load current. And all of a sudden, when there is a peak load current, the whole PV system will trip because now you have not sized your system for the load current. Instead, you sized your system for the average load current. Okay, and these two values, as we will see later on in the presentation, can actually differ by, quite some big amount. This is why I always recommend, if you know that you are installing a PV system in the region with weak grid, please always, look at sizing for peak load current. And if you are, sizing for a system that's in a very stable grid, go for the average load current. You are going to save, the consumer a lot of money by going for the average load current compared to the peak load current sizing. I think the best way to, explain a load profile design is to have a look at an example system. So what we're going to look at today is we're going to look at a single-phase grid-tied PV system with battery storage. Okay. The important thing to note here is single-phase grid-tied. Okay, this means that you have a grid available, and the second important parameter is a PV system, and the third important parameter is battery storage. Okay, so you want to achieve a system with a self-consumption of, let's say, greater than 90% in Johannesburg. Your consumer has 3 loads. The first load they have is a 1 kilowatt constant load, which occurs throughout the day and night. Okay. The second load is a geyser, and this geyser turns on 3 times daily for 1 hour durations each. So maybe it turns on once before sunrise, once at noon, and once after sunset. And remember, as my colleague Cyprian showed early on, we can also control with relays when we want to switch on a geyser and switch it off, etc. But that's as my colleague Cyprian did explain in his part of the presentation. Anyways, back to this section. The load will have an average running power of 1.5 kilowatts. So this geyser is turned on 3 times daily for 1 hour durations each, and it has an average running power of 1.5 kilowatts. The third load is a motor, and this motor has an average running power of 2 kilowatts. And for every 3 hours, this motor is turned on 20 minutes. Okay, so typical, motor could maybe be a motor for a pool pump, as an example. Okay, so this is the load profile of the customer. Here you can see the green block is the constant load of 1 kilowatt, which occurs in a 24-hour period, as indicated over here. The second load is a geyser, which, as said, turns on once before sunrise, once at noon, and once after sunset. So we're assuming that sunrise is at 6 a.m. and we're assuming that sunset is at 6 p.m., which I believe is a fairly good average, yearly average to look at. Okay. So here you can see before 6 a.m. the geyser turns on. Okay. Then at 12 p.m. noon the geyser turns on. Okay. As you can see, noon is not exactly at 12. It's a bit before and a bit after 12. Okay. So here you can see the second instance of the geyser turning on, and the third instance is after sunset, which we assume to be 6 p.m. as an average. And this is where we can see the geyser turning on after 6 p.m. Okay, for 1 hour. If you're looking at the load at the motor, which is the third load, that is indicated by these orange bars over here. And as we said, the motor will be turned on once every 3 hours for 20 minutes each time. So here we can see at 3 a.m. the motor, turns on for 20 minutes, then it switches off. Then after 3 hours again, which is at 6 a.m., the motor turns on, operates for 20 minutes, switches off. Then at 9 a.m., 12 p.m., 3 p.m., 6 p.m., 9 p.m., and then at 12 a.m. again. Okay, moving on. Now we basically need to do some important calculations. So what I did was I took the graph that was on the previous page and just added it onto this page just for easier referencing. Okay. So in order to calculate the daily energy, okay, that is consumed per day, we need to obviously look at all these different loads and basically, look at the daytime load, which we assume to be between 6 a.m. to 6 p.m. as a good average to look at. And then, go ahead with this calculation. So for the first load, which was a constant load, for the daytime running, it was 12 hours and you multiply it by 1 kilowatt, okay? Then you add the second load, which was the geyser, okay, which if you look at the daytime period from 6 a.m. to 6 p.m., the geyser only turns on once at this point over here. So this is why we then take 1.5 kilowatts multiplied by 1 hour. Then we need to add the next load, which is basically the motor. And because the question asks from 6 a.m. to 6 p.m., we need to look how many times this motor turns on between that duration. Here we can see 1, 2, 3, 4, 4 times. Okay, this is where we get 4 over here. However, please be careful. This motor only turns on for 20 minutes each time. So this is why we take 20 minutes divided by 60 minutes. Okay, then we multiply it by the load, which, as we saw earlier on for the motor, was 2 kilowatts. And once we add all these parameters together, we then get a daytime average load of 16.2 kilowatt hours. The next important parameter we need to look at is the nighttime load. So as we discussed earlier on, we assumed as a good average for Johannesburg, nighttime being from 6 p.m. to 6 a.m. Okay, this is where we have no solar irradiation happening. So for this period in time, we basically look at a base load, which is, as we saw earlier on, 1 kilowatt for 12 hours. Now the geyser, if you look at the geyser, it's turned on twice in this period. So once over here and once over here. So this is where 2 come from. The geyser is 1.5 kilowatt load, and that's where that value comes from. Then we need to add the motor values. So if we count how many times the motor switched on from 6 p.m. to 6 a.m., we can basically count 1, 2, 3, 4. Okay, so we basically count 4 times. And this is where 4 comes in as a variable. Remember, the motor switches on only for 20 minutes in every hour, and this is why we have 20 minutes divided by 60 minutes, and then multiplied by the average power of the motor, which was 2 kilowatts. When we add all these parameters together, we get 17.7 kilowatt hours. Here we can clearly see that the nighttime load is greater than the daytime load. The next parameter we need to calculate is the peak load current, okay, which is a very important parameter that you need in order to ensure that you select the correct hybrid inverter for your application. In order to calculate this, what we need to do is we need to look at the power rating of your loads. So in this case, we had a constant load of 1 kilowatt, which is 1000 watts, divided by your grid reference voltage, which, as the question said, it's a single phase installation. Hence, we divide it by 230. Okay, it's just a power equation. So power is equal to voltage over current. Okay, if we take current to the numerator and power to the denominator, this is how we get, and vice versa. This is how we get 1000 watts. So power on the numerator and voltage of 230 volts on the denominator. Okay, that was load 1. Load 2, which was the geyser, was 1500 watts divided by 230 volts. And then load 3, which is your motor, is 2000 watts divided by 230 volts. Okay, once we add all these currents together, we get a peak load current. Okay, remember, the peak load current will most likely occur in this period of year as an example. So here we can see all 3 loads are switched on. Okay, and in this particular point in time, so let's say at 12 p.m., the peak load current is 19.57 amps. Okay, the next parameter we need to calculate is your average load current. Okay, so again, as I said earlier on, we have power on the numerator and voltage on the denominator. The next parameter we need to look at is the average, okay, of this load over a 24-hour period. The first load is switched on throughout the day, and this is why we have 24 hours over 24 hours, plus the second load, which is 1500 watts over 230 volts. And as you know, with the second load, it's only turned on 3 times or 3 hours in a 24-hour period. And this is why we have 3 over 24. Then we need to add the next parameter, which was the motor. And the motor power rating is 2000 watts divided by 230 volts. Okay, and then what we have in brackets is basically what is the duration in a 24-hour period that this motor was turned on for. So as we know, the motor, it was 20 minutes out of 60 minutes, okay, multiplied by 8 occurrences. So 1, 2, 3, 4, 5, 6, 7, 8 over 24 hours. When we add all these parameters together, we get an average load current of 6.13 amps. Here you can see the stark difference between the average load current and the peak load current. And as I said earlier on, don't make the mistake of choosing an inverter where you have a very unstable grid for average load current. Rather go for peak load current. Okay, moving on. So how many panels are needed, and what size of inverter should you purchase or size for? Okay, so assume that we are going to use 400 watt panels, and this is your dimensions of your panel. So you have your length, which is 2.1 meters, your height, which is about 1 meter, and your width, which is about 0.04 meters. Okay, then the efficiency of this particular panel, let's say we have an efficiency rate of 21%. Okay. The next parameter that we need is that we need to see where the system is going to be installed. So as I said in the question, the system will be installed in Johannesburg. And if you go look at the solar irradiation map for Johannesburg, it's approximately, this is an average value, about 5.2 kilowatt hours per meter squared per day. Okay. So the next question you might ask is, what area of panels do I need in order to make sure that I achieve my power that's needed for the system? So what you need to look at is your energy for the day, which we already calculated in the previous slide, which turned out to be 16.2 kilowatt hours, all over the amount of, the efficiency of the panels multiplied by your solar irradiation, so your power per meter squared per day for Johannesburg, okay, which is the location. So we take 16.2, which, as I said earlier on, we calculated in the previous slide, all over the efficiency, which is given by the data sheet of the PV module, which is 21%, so it's represented as 0.21, multiplied by your power per meter squared for Johannesburg, which turns out to be 5.2 kilowatt hours per meter squared. Once you plug all these variables into this calculation, we're left with an area that is needed for the panels of 14.8 meters squared. So this means that I would need 14.8 meters squared of panels in order to achieve my daytime load. Okay. Where N represents the amount of panels required, so what you need to do then is take your area of your panels all over the area of a single panel. Okay, so we do know that the area of all the panels combined is 14.8 meters squared all over the area of one panel, which we can calculate. So it's 2.1 meters multiplied by 1 meter over here. So that we get from the data sheet. And we are then left with a value of 7. So this means that I would require 7 panels in this installation. However, it does not represent the area of the estate that is needed for these solar panels. As you know, with solar panels, we always need extra space in order to do servicing and to do connections and to do cleaning of the panels. And that's why it's always better to multiply your area of your panels by 1.3 in order to determine the area of the estate onto which the panels will be installed. So this will then give us a value of 9.1 meters squared. Okay, so what we basically do is we basically take the 1.3 and we multiply it by 14.8. So 1.3 by 14.8 would give you a value of 19.24 meters squared. So there's a small error over here. It's not supposed to be 9.1. It's supposed to be 19.24 meters squared. Okay, and that's the area of the estate. Okay, what would be the power of the inverter that you would need for this installation? So the power of the inverter would be your power of your panels, okay, all over the oversizing ratio that you're going to go for. Okay, so as you know, with Fronius inverters, they can take an oversizing ratio of 1.4 up to 1.5. Okay, so for example, with the Gen 24, we can take an oversizing ratio of 1.5. However, we don't stick at 1.5. We rather look at 120%, which is represented as 1.2, which would be a more economical value to look at. So we take the power of the panel, which is 7 times 400 watts over 1.2, and we then left with 2.3 kilowatts. Okay. Obviously, Fronius does not manufacture a 2.3 kilowatt hybrid inverter. What we do manufacture, however, is a 3 kilowatts and a 3.6 kilowatt Primo Gen 24 plus hybrid inverter. A 3 kilowatt Gen 24 will not work because basically the output current will be less than the AC max current of the load, which we calculated earlier on. So this is why I rather chose to go for a 3.6 kilowatt Primo Gen 24 plus hybrid inverter. With a 3.6 kilowatt Primo Gen 24 plus hybrid inverter, it will satisfy your maximum current need and your average current need for your installation. Okay, moving on. What is the size of the battery storage that would be needed for my Gen 24? So in order to determine the battery size, what we need to do is we need to look at the energy of the battery, which is equal to the energy that is needed at night all over the efficiency of the battery system. So the Gen 24 Plus hybrid inverter is only compatible with the BYD HCM battery, which has an efficiency rate of 96%. And this efficiency refers to the efficiency of charging and discharging cycles. Okay, so this is a really good and high efficiency rate of 96%. So we calculated earlier on the energy at night that was required, which was 17.7 kilowatt hours per day, all over the efficiency, which is 0.96. Okay, once you plug this into the calculation, we then get left with 18.4 kilowatt hour battery storage required. For the BYD battery, you don't get an 18.4 kilowatt hour storage per such, but what you do get is a 19.3 kilowatt hour HVM battery. So therefore, for this installation, I would recommend to go for a 3.6 kilowatt Gen 24 Plus hybrid inverter, which is coupled with a 19.3 kilowatt hour BYD HVM battery, which then is connected to, well, the inverter is connected to 7 400 watt PV panels. And this will really ensure that we can really cover the load good enough. Okay, that's it for my side of the presentation. However, if you do have further questions, you are welcome to refer to one of your contacts for sub-Saharan Africa, which is myself, Cyprian, or David. And you're also welcome to contact our international team as well. So that's the technical question number, the Sales International trainings, as well as after sales servicing. From my side, I'd like to thank you for attending today's webinar. We will send you the recording of the webinar as well as the slides, probably by sometime next week. Otherwise, again, have a good weekend, and we shall hopefully see you in the webinar next week, Friday. Goodbye.